The subject of this lecture is thermal energy. Here I will discuss the concepts of heat, temperature, as well as the zeroth, first, and third laws of thermodynamics. First, let's discuss the nature of heat. Early ideas about the nature of heat centered on the existence of a fluid that transferred between objects at different temperatures. That fluid was called caloric, that transfers heat between objects at different temperatures. At the time, that was the only possible explanation, for example, for a bucket of cold water left outside in the sun warming up. This primitive view of heat, of course, was due to the lack of sufficient technology to be able to better investigate and understand this phenomenon. Fast forward a few centuries, and in the 18th century, Count Rumford, who was the main engineer at a weapons factory, discovered that heat can be transferred without the presence of fire. And fire was then the only known source of high heat. And so with the evolution of technology, as you know, towards the end of the 18th century, the Industrial Revolution began. People developed enough means to be able to better understand and investigate and understand the nature of heat. And then they came up with the proper definition of what heat was. The definition of heat now is that heat is the energy that flows in or out of an object or between two objects due to difference in temperatures. This definition makes a lot of sense to us today because we know that if we leave a cold glass of water outside in the sun, it is going to warm up. We also know that if we leave a glass of warm water in the fridge, it is going to cool down. So there is a flow of heat due to difference in temperatures. The amount of heat energy gained or lost by an object is measured by the change of temperature of the object. So from this statement and the previous, you can see that there is a difference between the concept of heat and the concept of temperature. Fairly often, students confuse the two concepts. However, heat is an energy flow in or out of an object due to difference of temperatures. The units for measurement of heat in the metric system are calories or kilocalories. You may have seen food labels where the nutritional value is labeled in calories, spelled with capital C. That unit is identical to the kilocalorie. Let's define the units. What is 1 calorie? 1 calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. 1 kilocalorie is the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. And finally, in the imperial system, the unit for heat is the British thermal unit, or BTU, where 1 BTU is defined as the amount of heat needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. James Joule took the findings of Count Rumford and did a series of experiments and found that heat, energy, and work are related. He found out that work can be done to generate heat, and heat can be used to do work. James Joule performed the following experiment. He took a vessel and filled it with water. He also placed a thermometer in the vessel as well as a post with paddles attached to it. He attached the post to a hanging mass with a string running over a pulley, and then he let the mass fall down towards the ground. We know that when the mass is falling towards the ground, the gravitational force that pulls on that mass does work. The work done by the gravitational force is simply equal to the weight times the distance that this mass is going to fall. So the work will be equal to mass times gravitational acceleration times the distance of the fall, h. When the mass is falling down towards ground, that is going to cause this post to rotate, and that's going to spin the paddles in the water. So the experiment showed that the temperature in the thermometer went up when the mass fell down. So the conclusion that Joule came to was that the work done by the gravitational force on the mass to bring it down to the ground went towards heating up the water in the vessel. So he was able to establish a relationship between the mechanical work and the amount of heat generated in the water. The relationship between mechanical work and heat is simply known as mechanical equivalent of heat and relates calories to energy units, which are joules. 1 calorie is equal to 4.2 joules of work. So 1 calorie of heat produces 4.2 joules of work, or 1 kilocalorie of heat produces 4,200 joules of work. Let's do the following example of conversions between energy units and units of heat. Let's first convert 20 calories to joules. First, we start with the mechanical equivalent of heat for calories, and that states that 1 calorie is equal to 4.2 joules. So then from here, 20 calories can be converted into joules by multiplying 20 calories by 4.2 joules per calorie. The units of calories cancel out, and the final result is 84 joules. Now let's do a conversion in the other direction. Let's convert calories. Let's convert joules into calories. Let's convert 320 joules to calories. So I'm going to use the same relationship as before. My conversion factor will be different. So 320 joules are converted into calories by multiplying by 1 calorie and divided by 4.2 joules. The units of joules will cancel out, and the result is 76.2 calories. The final conversion will be from joules to kilocalories. Let's convert 6,700 joules to kilocalories. So for this, I need to use the other mechanical equivalent of heat, which was that 1 kilocalorie is equal to 4,200 joules. So this gives me 6,700 joules times 1 kilocalorie divided by 4,200 joules. The units of joules cancel out, and the result is 1.6 kilocalories, which is equal to 1,600 calories. Temperature is defined as an indicator of the amount of energy contained internally. This energy we are going to refer to as internal energy by an object. So what exactly is internal energy? Internal energy is energy that is comprised of several different kinds of energy. This energy is spread among the atoms or molecules of the substance which temperature we are measuring. For example, for the molecules of a gas, let's say, the internal energy could be made of the kinetic energy of translation of the molecules. So the molecules translate with some velocity v. They have some mass m, therefore they have kinetic energy. Another part of the internal energy of that gas could be also the kinetic energy of rotation of the molecules. So think of these molecules. This is a diatomic molecule. Think of it as a dumbbell that rotates about the central axis. It has a moment of inertia and also it has angular velocity. Another contributor to the internal energy could be also the energy of vibrations. So the molecule, the atoms, vibrate sideways like so. Those are vibrations. Those require some energy. So the energy of vibrations is part of the internal energy. Part of the internal energy could also be the potential energy of interactions between molecules in the gas, and so on and so forth. So all of these energies together form internal energy, and temperature is an indicator of the amount of that internal energy in the object. The tools that are used to measure temperature are called thermometers. There are several different types based on the way they operate. We have liquid thermometers, which are the common household thermometers. We have gas thermometers. We have resistance thermometers. We have infrared thermometers. And we have bimetal strip thermometers. All these thermometers operate on a specified scale of measurement of temperature. There are two main scales in existence in the world today. In the metric system, the Celsius scale. The Celsius scale, which is commonly used for everyday applications. And then we also have the related to it Kelvin or absolute temperature scale, which is used in various scientific applications. In the imperial system, we have the Fahrenheit scale. Both temperature scales, the Celsius and Fahrenheit, are based on two specific points of water. Those are the freezing point and the boiling point. The freezing point of water is 0 degrees Celsius or 32 degrees Fahrenheit, and the boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. So as you can see, there is difference between the magnitude, if you will, of a Celsius degree and a Fahrenheit degree. They're not equal to each other, which means that to do conversions between the two temperature scales, a formula relationship must be used. So let's see what that formula relationship is for conversions between the two temperature scales. First, to convert from Fahrenheit to Celsius, take the temperature in Fahrenheit, subtract 32 from that, and then multiply by 5 and divide by 9. So this conversion converts from Fahrenheit to Celsius degrees. Now let's look at the other conversion from Celsius degrees to Fahrenheit degrees. Take the temperature in Celsius degrees, multiply by 9 and divide by 5, and then add 32 to the result. Let's do two example conversions to illustrate the application of those formulas. So first let's convert 35 degrees Celsius to Fahrenheit. So that means that I'm going to use the second formula here. So I will simply substitute 35 degrees Celsius in the formula and calculate the result. So I get 9/5 times 35 plus 32, that is 63 plus 32, or that is 95 degrees Fahrenheit. Now let's convert 78 degrees Fahrenheit to degrees Celsius. To do the conversion, I'm going to use the first relationship here. I will simply substitute the temperature in Fahrenheit in here in the relationship and calculate the result. So I get 5/9 times 78 minus 32. That is 5/9 times 46, or that is 25.5 degrees Celsius. Later, when I talk about one of the thermodynamic laws, I will also discuss the Kelvin temperature scale real quick.